Our quest to understand the universe is as old as humanity itself. Long before we had laboratories and particle accelerators, we had our minds. We would look up at the night sky, a vast, glittering tapestry of stars, and ask the most fundamental questions. What is all this stuff? Where did it come from? And what is our place within it all? These questions were the seeds of both physics and philosophy. In the beginning, they were not separate disciplines. They were simply the pursuit of knowledge. A deep-seated human desire to make sense of the cosmos and our own existence. The ancient Greeks called this natural philosophy, the love of wisdom about the natural world. Think of the earliest thinkers like Thales or Anaximander. They weren't just philosophers in the modern sense. They were also our first physicists. They tried to figure out what the world was fundamentally made of. Was it water? Was it some undefined, infinite substance they called a pyrrhon? These weren't just idle guesses. They were the first attempts to explain the diversity of the world around us using a single underlying principle. This is the very same goal of modern physics today. We search for a theory of everything to unite all the forces of nature into one elegant equation. The tools have changed, but the fundamental question remains remarkably the same. This shared origin is incredibly important. It reminds us that science isn't just about collecting data and performing calculations. At its heart, it is a deeply philosophical endeavor. Every experiment we design, every theory we propose, is guided by underlying assumptions about the nature of reality. We assume that the universe is knowable, that it follows consistent laws, and that we can uncover those laws through observation and reason. These are not scientific facts that can be proven. They are philosophical positions. They are the bedrock upon which the entire magnificent structure of modern science is built, a testament to our enduring faith in the order of the cosmos. So, when we talk about physics, we are also, inevitably, talking about philosophy. The two are like dance partners, moving together through the history of human thought. Sometimes one leads, sometimes the other, but they are always intertwined. Philosophy asks the why questions, pushing the boundaries of our imagination and challenging our assumptions. Physics then steps in, using the tools of mathematics and experiment to test those ideas against the harsh reality of the natural world. It is a powerful partnership, one that has driven our understanding of the universe from the simple wonder of the ancients to the breathtaking complexities we explore today. Humans have an innate need to create order out of chaos. It's how we make sense of a complex world. We group things, we name them, and we put them into boxes. This act of classification is one of the most fundamental activities in science. Think about biology, where we have the beautiful system of kingdom, phylum, class, order, family, genus, and species. This isn't just a list, it's a map of evolutionary relationships. In chemistry, the periodic table is a masterpiece of order. It arranges the elements not just by weight, but by their electron structures, revealing deep underlying patterns that predict their chemical behavior. This drive to classify is deeply philosophical. When we classify things, we are making a statement about what we believe is important. We are deciding which properties are fundamental and which are superficial. For centuries, astronomers classified objects in the sky as stars, planets, comets, and nebulae. This simple act of sorting helped us understand the structure of our solar system and our galaxy. But these categories are not set in stone. The debate over whether Pluto is a planet is a perfect philosophical example. The argument isn't just about its size or its orbit, it's about what the word planet should mean. It's a debate about the boundaries of our definitions and how they shape our cosmic perspective. In physics, we classify the fundamental components of reality itself. We have the standard model of particle physics, a stunningly successful zoo of particles. We have quarks, which make up protons and neutrons. We have leptons, like the familiar electron. And we have bosons, which carry the fundamental forces. This classification is our best current answer to the ancient Greek question, what is everything made of? But it also raises new philosophical questions. Why these specific particles? Is there a simpler, more fundamental level of reality underneath them all? Are these particles real in the same way a table is real, or are they just mathematical descriptions? The act of classification, therefore, is not a neutral activity. It reflects our current understanding and, in turn, shapes our future inquiries. By placing things into categories, we build a mental model of the universe. This model allows us to make predictions and build technologies, but we must always remember that our classifications are human constructs. They are maps, not the territory itself. The universe does not care about our labels. As our knowledge deepens, our categories must evolve, reminding us that the quest for understanding is a dynamic process, a continuous refinement of how we see and order the cosmos. For centuries, the universe felt like a rather mysterious and unpredictable place, but then, in the 17th century, a figure emerged who would change everything. Isaac Newton. His laws of motion and universal gravitation were a revelation. Suddenly, the cosmos was not a place of whims and divine interventions, but a grand, elegant machine. It was a clockwork universe. If you knew the position and momentum of every particle at one moment, you could, in principle, calculate its entire past and future. The flight of a cannonball, the orbit of the moon, and the falling of an apple were all governed by the same simple, universal laws. This Newtonian worldview had a profound philosophical impact. It suggested a reality that was objective, predictable, and deterministic. The universe existed out there, independent of us, and it followed its rules with mathematical precision, whether we were watching or not. This idea brought a great sense of comfort and power. Humanity was no longer at the mercy of an incomprehensible cosmos. Instead, we were capable of understanding it, predicting it, and even mastering it. This mechanical philosophy fueled the Enlightenment and the Industrial Revolution, giving us a sense of control over nature that was previously unimaginable. It was a world without ambiguity. The philosophical implications of this clockwork universe were enormous. It led to the idea of determinism. If everything is just particles following fixed laws, what does that mean for human freedom? Is our sense of free will just an illusion? If our thoughts and actions are simply the result of a chain of cause and effect, stretching back to the Big Bang, are we truly responsible for our choices? This question troubled philosophers for generations. The universe, according to Newton, was a vast, impersonal machine, and we were simply cogs within it. Our future was, in a sense, already written in the stars, or rather, in the initial conditions of the universe. This view of a predictable, machine-like reality dominated scientific and philosophical thought for over 200 years. It was incredibly successful, explaining almost everything we could observe, from the smallest motions on Earth to the grand dance of the planets. It gave us a sense of certainty, a feeling that we were on the verge of a complete understanding of reality. The universe was a puzzle, but it seemed we had found the instruction manual. This beautiful, orderly, and deterministic picture of the cosmos was about to be shattered by a revolution that would force us to question the very nature of reality itself. At the dawn of the 20th century, physicists felt they were close to a final theory, but a few strange experimental results just wouldn't fit into Newton's tidy clockwork universe. When scientists looked at the world of the very small, the world of atoms and their constituents, reality started to behave in a way that was deeply strange and counterintuitive. Particles could be in multiple places at once. They could seemingly tunnel through impenetrable barriers. This was the birth of quantum mechanics, and it didn't just add a new chapter to physics, it tore up the entire book. The old philosophical foundations of certainty and predictability began to crumble. The core of this new quantum world is probability, not certainty. Unlike a thrown baseball, whose path is perfectly predictable, we can never know the exact position and momentum of an electron at the same time. This is Heisenberg's uncertainty principle. It's not a limitation of our measuring instruments, it's a fundamental property of the universe itself. The best we can do is describe the electron with a wave function, which gives us the probabilities of finding it in various places. The deterministic, clockwork machine of Newton was gone. In its place was a universe that seemed to be governed by the roll of a cosmic dice. This shift from certainty to probability was a massive philosophical shock. Albert Einstein famously disliked it, declaring, "God does not play dice with the universe." He felt that there must be some deeper, hidden reality that was still deterministic, and that quantum mechanics was simply an incomplete description. But for over a century, experiment after experiment has confirmed the probabilistic nature of the quantum world. Reality at its most fundamental level seems to have an inherent fuzziness, a built-in ambiguity. An electron isn't at a specific point until it's measured. Before that, it exists only as a cloud of possibilities. This quantum revolution forced us to abandon the simple, intuitive picture of the world we had held for so long. It showed us that the universe is far stranger and more mysterious than we could have ever imagined. The philosophical implications were profound. If the world is not deterministic, does this open the door for free will? If reality is only a set of probabilities, what does it mean for something to be real? Physics was no longer just describing an independent pre-existing world. It was beginning to seem as though the very act of observing the world played a role in creating it. Quantum mechanics introduced a truly radical and, honestly, mind-bending idea: the role of the observer. In the classical world of Newton, a measurement was, well, just a passive act. You could measure the temperature of a room, and your measurement did not change the temperature in any significant way. The room had a temperature whether you looked at the thermometer or not, but in the quantum realm, things are completely different. The very act of measuring a particle, of observing it, seems to force it to make a choice. Before the measurement, an electron might exist as a wave of many possibilities. The moment you measure its position, the wave collapses, and the electron appears at one single, definite spot. This is known as the measurement problem, and honestly, it's one of the deepest mysteries in all of science. It raises a profound philosophical question. Does a definite reality exist before we observe it? The famous physicist John Wheeler put it poetically, suggesting we live in a participatory universe. The universe in this view is not a finished story that we are simply reading. Instead, our observations, our questions, are helping to write the story as we go. The past of a particle, he argued, might not even be fixed until we make a measurement in the present. This challenges our most basic assumptions about time and causality. Think about the famous thought experiment of Schrödinger's cat. A cat is in a box with a radioactive atom. If the atom decays, a vial of poison is released, and the cat dies. According to quantum mechanics, until we open the box and look, the atom is in a superposition of both decayed and not decayed. This means the cat is, bizarrely, in a state of being both alive and dead at the same time. It is only the act of observation, opening the box, that forces reality to choose one definite state. The cat becomes either definitively alive or definitively dead. This seems absurd, but it really highlights the strange role of measurement. So what counts as an observation? Does it require a conscious human mind? Or can any interaction with a measuring device like a Geiger counter collapse the wave function? This is a point of huge debate among physicists and philosophers. Some believe consciousness plays a special role, while others argue that any large-scale physical interaction is enough to create a definite reality. Whatever the answer, quantum mechanics has blurred the line between the observer and the observed. We are not separate from the universe we study. We are deeply and fundamentally entangled with it. Our questions shape the answers we receive. One of the strangest predictions of quantum mechanics is a phenomenon that Einstein called spooky action at a distance. It's now known as quantum entanglement. Imagine you have two particles that are created together in a special way. Their properties, like their spin, are linked. Let's say one must be spin up, and the other must be spin down. According to quantum theory, until you measure them, neither particle has a definite spin. They are both in a fuzzy state of possibility. But the moment you measure one particle and find it is spin up, you instantly know that the other particle, no matter how far away it is, must be spin down. This is where the spookiness comes in. This connection is instantaneous. It happens faster than the speed of light. If one particle is on Earth and the other is in the Andromeda galaxy, 2.5 million light-years away, the measurement of the Earth particle instantly determines the state of the Andromeda particle. This appears to violate one of the most fundamental principles of physics, that nothing can travel faster than light. Einstein thought this proved quantum mechanics was incomplete. He believed the particles must have had definite spins all along, like a pair of gloves separated into two boxes. But experiments have shown that Einstein was wrong. This has profound philosophical implications for our understanding of space and reality. It suggests that the universe is not a collection of separate, isolated objects. At a fundamental level, it seems to be a deeply interconnected whole. The idea of locality, the principle that an object is only directly influenced by its immediate surroundings, seems to break down. Two entangled particles are better thought of as a single system, no matter how much space separates them. It's as if the space between them doesn't truly exist for that connection. This forces us to rethink what we mean by separation and distance. This interconnectedness, or non-locality, hints at a holistic view of the universe. It resonates with ancient philosophical and spiritual ideas that speak of the oneness of all things. Physics is now providing a scientific language to explore these ideas. It suggests that our common-sense view of reality as a collection of individual bits and pieces is an illusion. Underneath it all lies a web of connections, a hidden unity that binds the cosmos together. Entanglement shows us that the universe is more interconnected and far more mysterious than our everyday experience would lead us to believe. As we delve deeper into the mysteries of quantum mechanics and the cosmos, a new and powerful idea is emerging. Perhaps the most fundamental ingredient of reality isn't matter or energy, but something else: information. This idea, summed up by the physicist John Wheeler's phrase, "it from bit," suggests that everything we see, from particles to galaxies, arises from the processing of information. A bit is the smallest unit of information, a simple yes or no, or zero, or one choice. The it refers to every physical object and phenomenon. In this view, the universe is like a giant quantum computer, and the laws of physics are its algorithm. This is a radical shift in perspective. Instead of thinking of an electron as a tiny ball of stuff, we can think of it as a collection of bits of information, a bit for its charge, a bit for its spin, a bit for its mass. When particles interact, they are exchanging and processing this information. This way of thinking has already proven incredibly powerful. For example, it has shed new light on the nature of black holes. Physicists like Jacob Bekenstein and Stephen Hawking discovered that the amount of information a black hole can store is related to the surface area of its event horizon, not its volume. This led to the holographic principle. The holographic principle is the mind-bending idea that all the information contained in a volume of space, like our entire universe, can be described as if it were encoded on a distant, two-dimensional boundary surface. It's like a three-dimensional hologram being projected from a two-dimensional film. This suggests that the three-dimensional reality we experience might be an illusion, a projection of information stored on a faraway cosmic horizon. While this is still a speculative idea at the frontiers of physics, it's a profound philosophical concept. It challenges our very notion of dimensionality and what we mean by real. If the universe is fundamentally about information, it changes how we see our place in it. Our minds, our thoughts, our consciousness. These are also forms of information processing. It connects the physics of the cosmos with the world of computation and even biology, where DNA is a code carrying the information of life. This perspective suggests that the laws of physics are not just arbitrary rules, but perhaps the most efficient way to process cosmic information. The universe, in this view, is not just a random collection of matter. It's a meaningful information processing system, and we are part of its unfolding computation. The discoveries of physics don't just happen in a vacuum. They have profound consequences for society, for technology, and for our sense of morality. The same understanding of the atomic nucleus that helps us power cities with clean nuclear energy also gave us the capacity for unimaginable destruction with nuclear weapons. The development of the atomic bomb during the Manhattan Project was a stark and terrifying moment where physics and ethics collided. Scientists like J. Robert Oppenheimer were forced to confront the moral weight of their creations, forever changing the relationship between science and society. This raises a crucial question. Are scientists responsible for the applications of their discoveries? The pursuit of pure knowledge, of understanding the universe for its own sake, is a noble goal. But we can no longer pretend that this pursuit is separate from the world of human affairs. The power that physics has unlocked is simply too great. Every new frontier, whether it's artificial intelligence, genetic engineering, or new forms of energy, comes with its own set of ethical dilemmas. Physics gives us the how, but it cannot give us the why, or the should. For that, we need philosophy, ethical reasoning, and a shared sense of human values. Furthermore, physics continues to grapple with the age-old question of free will. The deterministic world of Newton seemed to eliminate it completely. Quantum mechanics, with its inherent randomness, seem to open a door for it again. But is random chance the same as freedom? If our decisions are based on the random firing of quantum events in our brains, are we truly in control? Or are we just subject to a different kind of determinism, a probabilistic one? The debate is far from over. Our sense of moral responsibility, the very foundation of our legal and social systems, hinges on the belief that we are free agents who can make meaningful choices. Ultimately, physics shows us the architecture of the universe, the rules of the game. But it doesn't tell us how to play it. The ethical dimension of science requires a different kind of thinking. It requires empathy, foresight, and a deep consideration of our purpose. It reminds us that knowledge is not the same as wisdom. As we continue to unravel the mysteries of reality, we must also cultivate the wisdom to use that knowledge for the benefit of all humanity. The quest for truth must be guided by a moral compass, ensuring that our power to change the world is matched by our responsibility to care for it. We began our journey with the ancient Greeks, who saw no distinction between physics and philosophy. After centuries of specialization, where science and the humanities drifted apart, we are now seeing a remarkable convergence. The deepest questions at the frontiers of 21st century physics are forcing us back to the most profound philosophical questions. What is the nature of time? What is consciousness? Why is there something rather than nothing? These are not questions that can be answered by experiments alone. They require a synthesis of scientific evidence, logical reasoning, and philosophical insight. The quest to understand reality is a holistic one. It's not enough to know the laws of physics if we don't also consider their implications for our lives. Science can tell us that we are made of stardust forged in the hearts of dying stars billions of years ago. This is a scientific fact, but it is also a deeply moving, almost spiritual, piece of knowledge. It connects us to the cosmos in a profound way. It gives us a sense of place and a story of origin that is both scientifically accurate and poetically beautiful. The search for truth is also a search for meaning. Integrating science, morality, and purpose is the great challenge of our time. We have the scientific story of the universe, a 13.8 billion-year epic of cosmic evolution. We have the ethical frameworks developed by philosophers over millennia, and we have the innate human drive for purpose, the need to feel that our lives matter. A complete worldview must weave these threads together. It must be grounded in the reality that science reveals, guided by the ethical principles that allow us to live together, and enriched by a sense of purpose that gives our existence meaning and direction. The journey is far from over. The horizon of our knowledge is always expanding, and with every answer we find, we uncover a dozen new, more beautiful questions. This is the wonder of the scientific and philosophical quest. It's a journey not to a final destination, but an endless exploration of a universe that is richer, stranger, and more magnificent than we can possibly imagine. By embracing both the precision of physics and the wisdom of philosophy, we continue this ancient and noble human endeavor in Tristau to understand in now vir det spartstho, kranja the cosmos, and in doing so, to better understand ourselves.